Separable differential equations, linear differential equations, and exact equations are all types of differential equations. They're specific types of differential equations and they fit a specific format. The world of differential equations and the possibilities of what a differential equation looks like is so much more broad than those three specific types of differential equation. Consequently, we need more tools to be able to solve more equations. One way that we go about solving differential equations that don't fit into any of these three categories is by using some kind of substitution. So today we're going to talk about solutions by substitutions, and we're going to look at three specific types of differential equations where making some kind of substitution will help us be able to solve the differential equation. One of the first steps that we take to solving differential equations when we're not really sure exactly where to start is we might try to transform them from the differential equation that they are into another differential equation that fits into one of the categories of differential equation that we have a solution technique for. The first type of differential equation we're going to talk about today is a homogeneous differential equation. Now, in order to talk about homogeneous differential equations, we need to first talk about homogeneous equations. If a function f possesses the property f of tx, ty, equals t to some power alpha, f of xy, for some real number alpha, then our function f is said to be a homogeneous function of degree alpha. So here's an example. Take the function f of xy equals x cubed plus y cubed. Then if I look at what f of tx, ty is, well, that's going to be t cubed x cubed plus t cubed y cubed. And hopefully, obviously, I can factor out a t cubed, and I'm left with t cubed times f of xy. So this is a homogeneous equation of degree 3. Now, say I have an equation g of xy equals x cubed plus y cubed plus 1. If I do the same substitution, I'm going to end up with t cubed x cubed plus t cubed y cubed plus 1. In this case, I can't factor out t cubed, and so g of xy is not a homogeneous function. So now that we have an idea of what a homogeneous equation is, let's talk about homogeneous differential equations. When we have a first-order differential equation in differential form, m of xy dx plus n of xy dy equals 0, we say it's homogeneous if both coefficient functions, m and n, are homogeneous functions of the same degree. If we have a homogeneous differential equation, then we can make a substitution that will create a separable differential equation, and will transform our homogeneous differential equation into a separable differential equation, and then we'll be able to solve it. So the proper substitutions to make for homogeneous differential equations are either y equals ux or x equals vy, where u and v are new dependent variables. Making either of these substitutions will reduce a homogeneous equation to a separable first-order differential equation. So let's take a look at an example. So let's consider the differential equation x squared plus y squared dx plus x squared minus xy dy equals 0. So the first thing I need to do is determine if this is a homogeneous differential equation. I'm going to do so by considering m of xy and n of xy and determining whether those two are homogeneous equations. So let's look at m of tx, ty and n of tx, ty, and see if they're homogeneous differential equations. And as you can see, m of tx, ty equals t squared m of xy, and n of tx, ty equals t squared of n x of xy. So both of these are homogeneous equations of degree 2. Consequently, this is a homogeneous differential equation. That means that we can use a substitution of y equals ux or x equals vy to simplify this into a separable first-order differential equation. As far as which of the two substitutions to make, either one will work, so you can pick your favorite or whichever one seems to be the most straightforward given whatever differential equation you're working with. In this case, I'm going to choose to use y equals ux. So when I substitute in y equals ux, I'm going to replace all of the y's with u times x, and I need to replace dy as well. To find what I'll replace dy with, I need to take the derivative of this equation. So I'll be substituting in for dy u dx plus x du. So now all that I have to do is make these substitutions into my initial homogeneous differential equation. This will give me the differential equation x squared plus u squared x squared dx plus the quantity x squared minus xux times the quantity u dx plus x du equals 0. So hopefully, pretty obviously, there's some simplification that can happen here by combining some like terms and doing some multiplication along the way. So let's do that. After expanding, we can see that we have a plus u squared x squared dx and a minus u squared x squared dx. So those will cancel each other out. And otherwise, the terms that are left are all unique. So I'm going to group them according to what derivative is taken with them. So I'll put the dx's together and the du's together. And then finally, in my first term with the dx's, I have an x squared term that can be factored out, and with the du's, I have an x cubed term that can be factored out. So I'll do that factoring. In doing so, I end up with x squared times the quantity 1 plus u dx plus x cubed times the quantity 1 minus u du equals 0. And now, this is a separable differential equation. So allow me to separate the terms. By dividing everything by 1 plus u, that's the term that has a u in it that's paired with dx, and dividing everything by x cubed, that's the x term that's paired with du. And when I do so, I arrive at x squared dx divided by x cubed plus the quantity 1 minus u du divided by the quantity 1 plus u equals 0. So now I can simplify the terms with the dx. X squared divided by x cubed is 1 over x, and I can perform long division with my du term, namely dividing 1 minus u by 1 plus u, and in doing so, I'll be setting myself up for something that's a little bit nicer to integrate. Now if I integrate, I'll be integrating dx over x and integrating 1 plus 2 divided by 1 plus u times du. If you're unsure of how that long division worked to get 1 minus u divided by 1 plus u simplified to 1 plus 2 divided by 1 plus u, please, by all means, feel free to reach out. I'm happy to provide more steps, but for the sake of time, I'm going to skip them for right now. So, if we do that integration, we end up getting to an answer of the natural log of x minus u plus 2 times the natural log of 1 plus u plus some constant. It's going to equal 0 still. So remember we substituted y equals ux to begin with. Now that we have solved the differential equation, we've gone through the integration part, it's time for us to substitute back in for our u value. So to figure out what to substitute back in, we're simply going to solve y equals ux for u. So we get u equals y divided by x. So everywhere we have a u, we're going to substitute back in y divided by x. This is going to give us the natural log of x minus y over x plus 2 times the natural log of 1 plus y over x plus some constant equals 0. So we don't really like leaving a bunch of natural logs hanging around, so we can eliminate them by moving all of the natural logs to one side of the equal sign, everything else to the other side of the equal sign, and then using properties of natural logs to combine them into a single natural log. And when we do that, then we can take e to the power of whatever's on each side of our equal sign, and that will eliminate our natural logs. So let's do that. And in doing so, and doing a bunch of simplification as well with stuff that we've talked about before, I have the quantity x plus y squared equals cx e to the y divided by x. And that's my solution to this homogeneous differential equation. The second type of equation we're going to consider today is called Bernoulli's equation. When we have a differential equation that looks like dy dx plus p of xy equals f of x times y to the nth power, where n is any real number, that's called a Bernoulli's equation. So you might notice that if n equals 0 or n equals 1, the equation is already linear, so we can use our linear solution techniques. If, however, n does not equal 0 and n does not equal 1, so it's anything else other than that, then we have a substitution of u equals y to the 1 minus n that's going to reduce the equation to a linear equation. So let's take a look at an example. So let's consider the differential equation x times dy dx plus y equals x squared y squared. Now, the first thing we need to do is rewrite it in the form given. The dy divided by dx equals p of x times y equals some function of x times y to the nth power. So let's rearrange this one so that it looks like that. And doing so is really as simple as dividing all of the terms by x. So now I have dy dx plus 1 over x times y equals x times y squared. So we have n equals 2, which means the equation is not already linear. So I'm going to use the substitution of u equals y to the 1 minus 2 power. Now you may be looking at this and saying, you don't have any y to the negative 1 power, so what good is this substitution going to do you? That's a good question. Instead, I have y's that I could be making a substitution for. So let's solve u equals y to the negative 1 power for y. So this gives me y equals u to the negative 1 power, which now gives me a substitution that I can make. Everywhere I have a y, I'm going to substitute in u to the negative 1 power. This gives me dy dx plus 1 over x u to the negative 1 equals x times u to the negative 2 power. Now hopefully you're saying, hey, wait a minute, there's still a y in there. And there is. It's with the dy dx. So we need to figure out what is dy dx in terms of u instead. Applying the chain rule, I get dy dx equals dy du times du dx. Now, dy du is going to be negative u to the negative 2 power. And since du dx doesn't have any y's in it, I can leave it as du dx, and I will. So wherever we have dy dx, we're going to substitute in negative u to the negative 2nd power du dx. Doing so, I arrive at negative u to the negative 2nd power times du dx plus 1 over x u to the negative 1st power equals x u to the negative 2 power. Having all of these negative exponents running around is really not great. So remember that the negative exponent really means that it's a fraction, and that's in the denominator. So this is really over u squared when we have u to the negative 2 power. So if I multiply everything by u squared, then I can simplify this a great deal. And I get negative du dx plus 1 over x times u equals x. Now, to make this set up in the linear form that I'm used to seeing, I'm going to multiply everything by negative 1 to arrive at du dx minus 1 over x times u equals negative x. Now for my linear differential equation setup, I have p of x equals negative 1 over x. This means that my integrating factor is going to be e to the negative integral of dx over x. Now, taking this integral, I get the natural log of x, so I'll have e to the negative natural log of x, which is equal to x to the negative 1st power. So we're going to use that integrating factor, and we're going to integrate d dx of x to the negative 1st u equals negative 1. And when we do that, we're going to get x to the negative 1st times u equals negative x plus a constant. So at this point, I can solve for u by multiplying by x. So I'll get u equals negative x squared plus cx. So remember, we made the substitution y equals u to the negative 1st power. So we're going to solve that for u, and we'll be making the substitution back in that u equals y to the negative 1st. So that's going to give us y to the negative 1st power equals negative x squared plus a constant times x. And we can solve for y simply by multiplying both sides by y and then dividing by the quantity negative x squared plus cx. So we get y equals 1 over negative x squared plus cx. And then all that we have to do is check to make sure that we don't have any singular solutions missing with this general solution that we found. And in fact, we do. When x is 0, it satisfies the original differential equation, but it does not work for this solution because then I'd be dividing by 0. So that's a singular solution that I need to be aware of. The final type of substitution we're going to talk about today is reducing to separation of variables. Now, we did already talk about a specific type of equation that does reduce to separation of variables, but here's a second one. So when we have a differential equation of the form dy dx equals f of ax plus by plus c, we can reduce it to an equation with separation of variables by means of the substitution u equals ax plus by plus c, whenever b is not equal to 0. So let's take a look at an example of this substitution. So consider the differential equation dy dx equals negative 2x plus y, the quantity squared, minus 7. We notice that this is a function of some constant times x plus 1 times y, so the constant 1 times y, So we can make a substitution of u for negative 2x plus y. And in doing so, we end up with dy dx equals u squared minus 7. Now, similar to the way we've had with all of our substitutions, it's not okay to still have dy dx in here. We need to instead be replacing it with du dx. So to find out what du dx is, we're going to take the derivative of our substitution equation. So taking that derivative with respect to x, we end up with du dx equals negative 2 plus dy dx. So to figure out what to substitute for dy dx, I'm going to solve this new equation that I have for dy dx. And it's going to tell me that I have du dx plus 2 that I should substitute in for dy dx. So let's make that substitution. So now I have du dx plus 2 equals u squared minus 7. If I subtract 2 to the other side, then I have du dx equals u squared minus 9. Now, u squared minus 9 equals u plus 3, u minus 3. And so this hopefully looks like it's really asking for separation of variables and some partial fractions to be used. So to separate our variables, we would multiply by dx and divide by u squared minus 9. So we would have du over u squared minus 9 equals dx. And now we would use our solution techniques for separation of variables. We would use some partial fractions here to make this something that we could integrate. And we would come up with a solution in terms of u. And then, just like we've done in the two examples previous today, we would substitute back in for u, putting our negative 2x plus y in place of any u's that are occurring in our final solution.